2025 MTV Nuclear Engineering Summer School is going to be related to radiation imaging. Today's talk will be given by Will Heriot. He's one of the PhD students here in the University of Michigan in Professor Sarah Potsy's research group. Before I hand it over, just as a quick reminder regarding how we're going to handle questions here today, feel free to ask any questions that you have in the Q&A, and then at the end of the talk, the speaker will be going over them with me. So again, if you have any questions, feel free to put them up in the Q&A. Otherwise, until then, Will, go ahead, ready whenever you are.
All right. Thank you, Ricardo. Well, yeah, my name is William, and as Ricardo said, I'm a PhD student in Dr. Potsy's group, or the Detection for Nuclear Nonproliferation group. And I'm here to talk to you guys about the radiation imaging methods. So we'll start with some motivation. There we go. So the motivation, at least I have and my group has for using imaging systems, is mainly in search and emergency response and verification. For search and emergency response, current deployed detectors usually work by measuring like relative count rates. So the Geiger counter, as you get closer to the source, beeps faster, or because there's just more signal it's picking up. But it's very bad at like filtering out background fluctuation, being sensitive to specific energies. And if you use an imaging system, you can filter out background radiation and also give yourself a direction toward the source of radiation, and which is super helpful while still being the kind of same form factor. This is also, we also want to use this for verification. So imagine an inspector trying to monitor or verify the location of a source, and he just needs something portable, something that can be easily used. Sometimes there are like places where he has to do monitoring and he can't plug it into an outlet, or he just needs to have a long battery life. Detectors, like imaging systems, can be very low power, so and can be handheld, so they're pretty useful for that. You also might want to deploy maybe a larger passive system that constantly monitors the source. Like say you just had a warhead sitting in a monitoring facility, like a storage facility. You would probably want a imaging detector on it at all times to kind of see if someone goes in and tampers with the warhead or removes it. You can see the image of the active material, especially the material inside the warhead, change, which, as you can see, would be super helpful for making sure nothing bad happens. I will mention also that radiation imaging is very big with medical imaging, but as that's not really my specialty, it's not something we'll go too far into. We'll mostly be focusing on radiation imaging systems in regards to nuclear nonproliferation. So we'll at least do a brief overview of radiation imaging methods. So we can generally classify it into three categories. There's transmission imaging, which think like an X-ray, right? Where you have an external source that's kind of known and prepared, and then you measure the attenuation. So I shoot an X-ray beam at my chest, and then you measure the attenuation my bones make, and that shows a picture of my rib cage, right? Because my rib is more dense than the soft tissue. The main thing I work with is emission imaging, which is where we measure the radiation emitted by a direct source that may or may not be known, passively acquired. And so this would apply to like neutron scatter cameras and Compton cameras. And then there's induced emission imaging, where radiation is induced with a source or object. So it'd be very similar to emission imaging, but instead of imaging something that's radioactive just naturally or the way it comes, you would instead use something like a linear accelerator or a neutron generator to kind of induce fission or some sort of radioactive reaction in that object. And of course, this is not an all-encompassing categories for all kinds of imaging. There's PET scans, SPECT, neutron tomography, CAT scans that are honestly like complicated enough to warrant a talk on their own. So let's get right into it. Let's start with a neutron scatter camera. So in order to make a neutron scatter camera, you at least need two detectors, but we'd rather prefer more. And we would measure, so a neutron would kind of come in, hit the first detector, and scatter off of it and hit a second detector. And so the vector we draw between the two interaction points is what we're going to call the lever arm, and the parts and the information we wish to get from this interaction are its location, so we can draw that vector, its time, because we want to figure out the energy of the neutron after the first scatter, using time of flight, which we'll get into later, and then the individual energies of each scatter, particularly the energy of the first interaction. And so, as I've already mentioned with time, the two things we care a lot about is the energy of the neutron before the scatter and the energy of the neutron after the first scatter. To get the energy of the neutron after the first scatter, we can do some classical kinematics, and just first we get the distance between the two source interactions positions, divide by the time difference, get velocity, and then our classic kinetic energy formula. The mass of a neutron, plug it in, and we get the kinetic energy of the neutron traveling between the two detectors. Perfect. And so now we want to get the energy of the neutron before the scatter, which is real. We have the energy of the neutron deposited in the first scatter, add that to the time of flight energy, we have the neutron before the scatter. And this is great for neutron spectroscopy too. So every neutron scatter camera doubles as a neutron spectroscopy detector. And so something that's very nice about neutron scatter cameras that Compton scatter cameras don't have is that in situations where we have to most neutron sensitive detectors are mostly hydrogen, but if you assume that the neutron scatters on hydrogen, which just the way the cross sections work out is usually true, honestly, almost always true. We just have a very simple equation where we just put the energy after the first scatter and the energy before the first scatter and that ratio, and then the cosine, and that is equal to the cosine squared of the scattering angle, which is going to be useful for getting the cone projection, which is what we'll kind of get into in a couple more slides. But first, let's go about gamma imaging. So neutron sources are very valuable for special nuclear material, but not as common as like photon or gamma sources. So how do you find that out? So as usual, we have two detectors, but you'll notice instead of two of the same detector, we have just, honestly, I think the main constraint is that the second detector at least has to be a higher Z material. But I'm getting ahead of myself. I'll do more on that later. But we care about the same things: energy deposition, time of interaction, and the interaction location. And our equation's a little bit more complicated, but this is just the Compton-Scatter equation. It might have been covered in a previous lecture, and if you missed that, the Compton-Scatter equation is a very common thing that can be looked up. But yeah, so the main assumption we make with this equation is that E1, the energy deposition in our second detector, is the photoelectric effect. This, in reality, is not always true, and is also why we want a high Z detector, because this will not work if your second detector is a low density, and by high Z, I mean like the atoms it's made up of have a lot of protons and neutrons, or yeah, a lot of protons in it. So like cerium bromide's a lot better than just a detector made out of hydrogen. That makes sense. So where was I? So yeah, so if we assume the second event is the photoelectric absorption, this equation holds true because that is basically just telling us the energy after the first scatter. So what E1 really is in this case is energy after the first scatter, and E is the energy of the photon or gamma before the first scatter. But plug it in, we have the mass of electron, speed of light for C, and we get the same thing we're looking for, which is cosine squared theta, which is our cone projection. Something worth kind of noting is that a method we can do to get around the fact that sometimes the second interaction will just be a Compton scatter again, is that we can gate. We can just if we know the energy of the source we're looking for, we can just limit it to our events where E is equal to the expected energy of a source. So that's very useful. It's very important that we get the sequencing right. So we need very fast detectors. So very slow inorganics certain inorganic detectors might be too slow. Then I'd be good enough. So, and the speed of the time difference between this interaction is going to be on the order of like hundreds of picoseconds. So the time resolution of your system should be around that. And okay. So I've mentioned earlier about cones. And so from the angle and the lever arm, we can project a cone of possible locations because we don't get an exact direction from that, but we get a cone of possible directions it could have came from. And what happens is that if we sum these cones, or we project these cones onto a surface and sum them, they will eventually overlap in the spot that is the true source location. And in the beginning, it's a little bit wonky, but as more cones are kind of added to the image, you'll see it kind of slowly converges to 0, 0, which is the true source location in this case, but it'll converge on the true source location. You can also do this. You don't have to do this projection, can be done. We traditionally do it, and a lot of what we're going to show you is going to be a sphere around the detector, but can also be done on different surfaces, we'll talk about a bit later on when you'd want to do that. So So in order to get our image, so we need to have a surface to project the cones onto, because like the cones are a 3D object, I need this an image, which is a 2D object. How do I get that? So this is so what we do is that we imagine a 3D sphere around a detector, we pixelate it, and then we convert that into a 2D matrix. And so each of these individual pixels you see on the sphere correspond to a pixel on our 2D matrix. And just the y is the altitude angle, and the x is the azimuth. So how do we kind of get there? Because that's kind of complicated. And forgive us, but this is probably going to be the most math-dense part of the talk. So first, we need to convert from spherical coordinates to Cartesian coordinates, or yeah. And then from there, we need to calculate our lever arm. So we have our vectors. So we just get the vectors. So we're taking the distance or the vector between the two interaction positions and then normalizing it. And then after that, so we want to figure out, and so we need to calculate how, and so what we kind of need to do is we need to calculate what is the kind of intensity or probability that the particle came from that specific pixel. So we also need to calculate the angle between the lever arm and a given pixel. So just pick any random pixel on there. We'll need to calculate the beta for that. The alpha is just going to be our cosine squared of theta, which is what we got from a measured event. And also, we need to kind of have a complicated cone projection equation. And I'll try and break this down, but this is a Gaussian broadened equation. And so the idea is that we have some error in the calculation for a scattering angle and some error in the angle between the lever arm and a given pixel. And that's just based off of time resolution, energy resolution, position resolution of our system. And so we can't specifically say this exact point is where we expect it to come from. We have to kind of give a broadened distribution. So if we look at how beta is subtracted by alpha in the numerator term, that means that if both of those, so if both of those are like the same or very close to each other, that kind of zeroes out the whole equation, and then it becomes e to 0, which is just 1, would be our highest point in our equation. However, and so as b becomes more different from alpha or scattering angle, the equation starts to drop off in intensity sharply. However, if we divide that by our errors, that how far off it'll drop off sharply will kind of take a bit longer and it'll broaden it. And I understand it's a bit difficult, but I think some of the following demonstrations and slides will kind of give more images to that idea. So let's just talk about what cone projections look like. So what we have here, the red is going to be a cross-section of a sphere. And we have two detectors right in front of each other, and we have interaction at like x is equal to 5, and interaction is x equal to -5. So basically, an interaction directly in front in the x plane that goes right through. So we calculate our cosine squared of theta to be 0.05, which corresponds to 45 degrees. And so from there, we have our cross-section of a cone, and that projects itself onto the sphere. So what does that mean? So how that would look with just one cone on our image, it looked like this. And so as you can see, our kind of lever arm would be at 0, 0 in this case. Because imagine, right, you subtract those two position vectors, it's just a 0, 0 vector. So it's right at the middle, where theta and phi are equal to 0. And every point where the angle would be 45 degrees away from that, you'll see the kind of peak of our Gaussian broad projection. And because we are assuming 10% uncertainty, instead of being a perfect thin line, it broadens out and it broadens out as we go, well, we might actually mismeasure the angle and it could have been at 49 degrees, or yeah, 49 degrees. And this is it might have been, and this corresponds to our level of uncertainty when it might have been that too. Let's see. So let's kind of just do another case. So instead of having it be on the same x plane, what if we have it on the y plane? And so basically we're just rotating the lower arm so it is pointing at set same at 45 degrees, or I guess not, sorry, 90 degrees in the azimuth, but still at 0 altitude. And all we really did was shift the cone that's 90 degrees to the right. So it's at 90 degrees in the azimuth. We still have our scattering angle of 45 degrees, same uncertainty. And all we did was just change the lower arm. I just kind of drifted it. So we've kind of been viewing everything at z is equal to 0. So if we instead stack the detectors on top of each other and look at them in the z plane, and as you can see, our cone projections actually facing directly at the screen and kind of draws a circle around, and just draws a circle like an equator, but except a bit higher out at the azimuth along the sphere. How that would look like if you draw this out might be a bit intuitive, but imagine you had a sphere, drew a circle around at a constant altitude, and then unraveled that sphere. It would actually just end up being a line. And that's kind of what we see here. So basically, cones that have the cones that are like just at a constant altitude, and at a constant altitude and generally wrap around from the edges of our sphere show up as lines. That makes sense. Okay. So and let's kind of talk about how relative uncertainty, having higher errors affects our cones, and how scattering can affect our cones. So a higher relative uncertainty, as you can expect, gives a poor estimate. And so as I was talking earlier, the rate at which the broadening happens, so the broadening happens across a wider distance or wider angle at higher relative uncertainties. And as you can see, this kind of more intense red region spreads out at higher relative uncertainties. What's less intuitive is that this happens in reverse for lower scattering angles. And I think this is more of like a trigonometric effect, the fact that as the cone is sharper, like with a sharper confined cone angle, the broadening effect is kind of more pronounced. So we've looked at a ton of just single cone cases, but we take away anything from this is that you can't do neutron or Compton scatter imaging with just one cone. What you do is that you take hundreds, tens, hundreds, thousands, basically as many cones as you can, and have them all overlap on a single point. And so what happens if I vary the uncertainty and the scattering angle on that? How would that affect the kind of point where they overlap? So what's actually very interesting and intuitive here is that like limiting our uncertainty doesn't have a drastic effect on the image confinement. It has a noticeable one, as you can see, as we reduce the uncertainty of our cones, and this is all simulated data. We do get a reduction in like the width of our like cone area, but it's not that drastic. However, if we instead limit the scattering angle, so this is all the same data set, but we're actually reducing the cones by filtering out scattering angles that are basically that are outside the range kind of shown on the right side of the screen. So if we have scattering angles can only go up to 180. So we filter out basically none of them. And then, okay, everything less than 25 degrees and above 155 degrees, we filter out. Oh, it comes notably smaller. And we filter out 40 to 140 degrees, actually becomes much smaller. So just putting a filter on your events improves the image a lot more than reducing your measurement error or the fidelity of your system, which is a lot harder to do than just applying a filter. Okay. Now let's talk about how lever arm distribution affects our detector. So from the scattering angle thing, so I guess the point of the scattering angle thing and lever arm distribution thing is that you need to design your detector array so that you not only, so you have a small range, a range close to 90 degrees of a confined range of scatter angles that are possible with your detector. And you also need to design your detector array so that you have an even lever arm distribution. So if we remember, lever arm is just the the interaction vector between our two interaction positions from any detector 1 and detector 2. So basically, you basically just need to have an even spread of detectors. and you need to have a lot of detectors. And so with this sample intensity scatter map, which would be an ideal one, evenly distributed and has plenty of possible lever arms, you get a fairly reasonable image. However, if we reduce the amount of lever arms, so if you have less detectors, you'll end up having less possible lever arms because there's less possible vectors you can draw between your detectors. You'll actually get artifacted images. So all of this data was generated with a point source with its true position at 0, 0. But as you can see, it has these artifacting on its edges. It has its growing spikes. And all these spikes only kind of go away and go to a more true source, which is obviously converged on a point which has an evenly spread of uncertainty evenly around it. Because like the reality of the reality of the imaging is that there isn't really a chance the source is at those spikes, but those spikes end up doing so because when you are limited in lever arms, cones just tend to overlap. And if that doesn't make sense, don't worry, we have a slide that kind of describes that in a couple of slides. But first, I want to point out that having an even distribution of lever arms is also important. So instead of changing the number of lever arms we have available, we will just change it so they're unevenly distributed and can only happen in like the kind of a specific range as you can see on the right. So instead of having a even distribution, we'll have them only on these edges confined to these angles. And remember, it's all just a single point source at 0, 0. Instead of it appearing like that, it appears instead like a rod that's a lot longer. So it's very important that you set your detector geometry to have an even spread of possible, like an even spread of possible lever arms, and probably even more important than confining the scattering angle. So honestly, this is a very kind of abstract geometric kind of problem. So let's kind of create a simple equation, like a simple situation. So we only have one lever arm now, basically a system with only two detectors. And then we have four cones. Our source is still at z is equal to 0. And as you can see, we have four different cones with different, so each of these red lines is a different lever arm along this kind of lever arm distribution. And we have them all overlap at this position. However, as you can kind of see, all these cones don't just interlap at the source location. They interlap at multiple different areas around it. And so how will that affect the image? Well, turns our point source into a disk, which is very different from what we expect. And which is, well, it just isn't what we simulated. Like the source doesn't really look like that, but it says, oh, the source could be not only be at 0, 0, but the source could be at like, in this case, it would be at like negative 20 degrees, negative 25 degrees, anywhere along that line. So it's very important to have plenty of detectors in your array. So enough of the theory, let's kind of get into kind of the application example in the research project I currently work on, and also Cardo does. So an example of a good or dual particle imaging system would be the HDPI. And so we have 12 organic glass bars surrounded with a diffused Teflon reflector, which is basically just keeps the light from escaping the bars, because the light is generally how we measure the energy deposition and the position. So organic glass is a scintillating material that is mostly carbon and hydrogen. And what happens is when a neutron or a photon interacts with it, it deposits energy that causes scintillation light in that area. And that scintillation light can be collected, is proportional to the energy deposited in that detector by the particle. And that can be collected at the top and bottom of the spheres. What's also really nice about OGS is that it's actually very capable of discriminating between neutrons and gamma events just by the shape of the pulses. So scintillating light is a bit slower for neutrons, and so the decay pulse is better. So that's very handy when you want to measure or target both neutrons and gammas and kind of separate events between the two. So as we kind of mentioned, unfortunately, organic glass is made out of both carbon and hydrogen is not good enough on itself for gamma imaging. So we have also 8 cerium bromide bars in the corners, and cerium bromide is significantly higher Z. And so even though they're a lot smaller active volume, they still are very effective for collecting events. And so those also have a wrapping. I think it's more like like just a metal casing instead of Teflon, just kind of what we came in when we ordered them. And so how we kind of get this is how do we collect the light they generate is that we use silicon photomultiplier arrays. We have one on the top and one on the bottom. And basically how we kind of get the position resolution in the HDPI is that we have a single bar mounted on both the top and bottom. And the ratio of light collected on the top will be higher if the event is closer to the top. So just from the ratio of light collected on the top and bottom SIPM, you can determine its Z position. For the X and Y positions and for the Z position of the cerium bromide, we do just kind of assume it happens in the center. And because these things are so small, it ends up working out for our image. The position resolution there is nice and is in fact, yeah, that's pretty much it. So talked about LGS doing PSD. And also, I think a nice thing that I think if you kind of do a lot of digging around in this field, you notice that there's this difference between simple back projection images, which is kind of what we've shown up to so far, and models that have kind of been reconstructed with a converging algorithm called LMMLEM. And MLEM stands for maximum likelihood estimation. Maximization. Redundant, I know. And all that basically does is just basically basically focuses the image or reconstructs the image to focus on like the hot spot or the highest points in the image. All right, so let's talk about how gamma imaging occurs in this specific system. So incoming photon comes in. Compton scatters off of one of the organic glass bars because it's low Z. You have a scintillation light signal that goes to the top and the bottom SIPM. It scatters into one of the cerium bromides. And the cerium bromide also has a photoelectric absorption effect and generates light that is absorbed by the top SIPM. I think so something that wasn't intuitive when I first learned about this is that this is a fairly rare event, but when you have enough gammas kind of going through, it'll happen quite a bit. But I think one of the things to kind of think about when making and designing neutron and Compton scatter imagers is do you have enough detectors in the active volume in your array to get a high enough efficiency? I think I'm getting off track. Now, if instead we wanted to do a neutron event, so we have our organic scintillator. It's fine if we have two of the same detector. We don't really care about Z. We just care about having a lot of hydrogens. So our equation is correct. And we just have C. I'll wait for it to cycle. Let me check my time. Okay, yeah, we're on track. So a neutron kind of comes in, scatters off the first organic glass detector, and then scatters off the second organic glass detector. And then from there, we can get the Z position, get the angles, and then we can get the Z position, do time of flight analysis to get the energy for and after the scatter, sum that, yep, and then can get an angle, direct that onto a cone. What's also worth noting is that cerium bromide is blind to neutrons, so if a neutron scattered off of cerium bromide, we couldn't see it if we wanted to, effectively. But yeah, so so what happens if I use this with active sources? What do I get when I measure this? So we kind of have two situations or measurements we've cherry picked to kind of show you guys. And we have a cesium source, cesium-137, placed 50 degrees at 23.4 centimeters away. And then we have a sodium-22 source placed at negative 50 degrees in the azimuth, 23.4 centimeters away as well. And if we're not familiar, cesium is a very common source used in detector characterization and calibration because it is the most simple gamma source you can find. It just decays, and one of its only gamma emissions is a gamma ray at 661.7 keV. So we just kind of look for that image, where we just look for that photon energy, and that's super helpful for us. Sodium-22, on the other hand, is a bit different. It actually has two, I think one at 1,274 keV, and it also uniquely emits a positron, which kind of decays and releases two 511 keV gammas in the opposite direction. And what's kind of notable about that is that just because the energy of the 511 is lower and more of the positron decay happens, it basically, we just treat it in this case as a source of 511 keV gammas. And so for the neutron measurement we'll show you is that we have placed kind of a cesium source, which is just the same as the last one, but and even though it's not a neutron source, we have it there just to show that we don't see it when we try and look for photoneutrons. And then we place two neutron sources, which is we have Californium-252, which is a very common spontaneous fission source, just is unstable enough that it just enters fission spontaneously, but not really at a rate enough to kind of, generate power or be useful in the power generation regard. But for doing research and studying fission and neutron generation detection, super useful. We placed that at 25 degrees and put it 58.4 centimeters away. Then we have a different neutron source, plutonium beryllium, which is an alpha N source, which means we rely on the alpha particles generated through plutonium decay. That gets absorbed into beryllium, and beryllium releases a kind of a neutron as a result of that alpha absorption. And so we placed that a little bit closer to try and balance it out. We placed that a little bit closer because we were trying to balance out the relative neutron emission rates at negative 25 degrees azimuth. All of these are stuck at 0 altitude, just for simplicity's sake. So let's look at what the gamma ray measurement images look like with just 18 seconds of data. So it's not the best images you've seen, but it's quick. And so we filtered out only events within a certain energy, so the total energy, so to make sure that we only get events that have a photoelectric effect in the second thing. And we also want to make sure we're not getting events from the cesium, because we just want to look for the sodium-22 in this case. We apply an energy gate, which is 511 keV, plus or minus 33 keV, because our detectors do have an energy resolution. And so the light output response that we measure isn't exactly going to be 511 MeV every time. It might plus or minus about 33 keV in this case. And so it's not perfect, but you can kind of see on that direction, there's a sodium-22 source. And so we do the same for the cesium. We do it at 661.7 keV, plus or minus. It's the spread we get from the energy resolution. And it's a nicer image. It's a stronger source. And we were able to kind of pinpoint, yeah, there's a detector about in that case. And like, as you can see, like the source, the location where the source probably is usually the dark red part in the middle. So we can tell there's two different sources within 18 seconds of measurement. Pretty good. What happens if we measure for longer? So if we go for about 2 hours, and I think we apply MLEM, we might or might not. We have much more confined images, and we actually can accurately find the source location within 1 or 2 degrees, which is very good. And so the black circles correspond to where the source would be in like real space. And as you can see, our kind of dark red, most probable area is where the source is, or where we think, or where the system predicts the source is. So we're very happy with those results. We're very happy that we can see 2 different images. So you're able to kind of transfer the theory and the technology very well. However, as a non-proliferation group, the real meat and potatoes of what we like to think about is neutron imaging, because if you can find where there's neutrons, you can find where there's special nuclear material. So with a similar amount, 2 hours of measurement data, and we can't do convergence and we can't gate on energy with neutrons just because most neutron sources are very rarely monoenergetic. So because PUBI and Californium-252 kind of have a spread of neutrons, we just kind of have to image all the events together and see if we can tell the difference. And even without gating, we can still very clearly see that there's 2 distinct regions. Because we didn't match the efficiency, like we tried to match the detection efficiencies of each source to be the same. PUBI ended up being a bit stronger in this case, so we see that's a stronger source. But I can very clearly see that there is a separate kind of probability circle that represents, oh, there's probably something different there. So we can kind of go there. We kind of, if we look in that region and find like the highest point in that sphere where Californium-252 is, that's where we estimate the source position. And then the highest point overall is going to be where we estimate the PUBI to be. And so when we do that and we found these 2 sources from, I guess, 40 to 50 centimeters away within 1 or 2 degrees of error. Pretty satisfying. And we don't see really any effect from the cesium because we're able to filter that out using the pulse discrimination properties of organic glass. Very good. So now that we've made a system, what else can we do with it? So I think one of the main weaknesses is that plots, like in back projection images, as we kind of see, there's a lot of background to think about. You have to be very comfortable with spherical transformations onto Cartesian coordinates. There's a lot of weird artifacts you just have to know about beforehand and know that, oh, it's a result of because the detector was designed this way, you'll find this artifact, but that doesn't mean the source is actually there, you know. And so what if we instead kind of took that image and projected it not on a sphere around the detector, but in a mixed reality environment? Also, we only have a direction vector, and sometimes you kind of want to know how far the source is away, how far away the source is. So instead of using simple back projection, what if we use like a triangulation and 3D imaging method instead of projecting it onto a sphere? What if we just have the cones go out through, I guess this would be voxelized space now, and see where they intersect? First, we'll talk about the mixed reality visualization pipeline. So generally how the pipeline works for the detector is normally we just have a detector system that produces an analog pulse that we send to an analog to digital converter, and then we take that to an acquisition PC. Which is how we kind of discriminate between neutrons and gammas and kind of create the image, do all most of the heavy lifting of the math. And what if we, after we make that projection, what if we send that, or we calculate those cones, what if we sent it to a mixed reality headset, which is we use the HoloLens 2 from Microsoft. We chose the HoloLens 2 because it was a well-developed system that could create a live spatial mesh of the measurement environment, which basically means you look at a surface with the goggles and they kind of know there's a surface there. And then you can project cones onto that surface, just kind of see where you're kind of going with this. And so kind of what we have our system do is that we basically put this headset on, and then you can tell it whether you want to look for neutrons or gammas. It renders a spatial mesh, and you can look at just a 2D polar image, or you can just or if you just look at the area around it, you can see hotspots generated by where the vectors from the image intersect with the spatial mesh and show you, oh, there's probably a source either at this surface or behind this surface. And you can also, because every Compton and neutron scatter camera is going to be also just a regular detector system anyway, you can also do energy spectroscopy pretty well. And of course, we'll have accessibility option for color blindness, because the point of this system is to make sure not just scientists can use this, that anyone, like emergency response teams, military soldiers, can just use this system. And yeah, if you want to read more about the mixed reality visualization pipeline, I'll have Oscar Patari's and Ricardo Lopez's paper in the slide and like on the slide, and I'll send out the slide afterwards. You see it, but also if you just search this title, you'll be able to find the paper pretty quickly, or just put in the DOI number, right? So let's see the system in action. So we set up a mock inspection scenario where we have 3 barrels. And the inspector was told, oh, there's radiations, there's like special nuclear material in all of these barrels. So we kind of have a true barrel where we have a shielded neutron source inside the barrel, which would be emitting a lot of gammas. We have one of the barrels be empty because, oh no, something's being hid from us. And then we have one of our barrels with a gamma source in there where they're kind of thinking that, oh, if they had a Geiger counter and they just measured the barrel, they go, oh, there's something radioactive in there. But maybe you can trick them into thinking there's special nuclear material in there instead. However, we'll see the HGPI kind of cut through this and kind of give us detailed information on what's inside these barrels without ever having to open them. So just to kind of get the spoiler alert and what we expect to see, we imaged, so we ran this for a couple hours. And then when we imaged it on sort of coordinate space and then applied MLEM on it, we have a clear region where the californium is, and we have a clear region where the gamma ray is. What's kind of note is that our californium is a bit of a rod source, so that's why it's a bit elongated. And the gamma ray is like a small volume. So that's why it's kind of centered there. So it's kind of placed at those locations in space where phi is the altitude, theta is the azimuth, very similar to what we've kind of seen before. And basically it corresponds to these locations we see in these images. So let's see how Ricardo set this up. So all Ricardo has to do is put on the headset. And yeah, so he presses the power button to turn it on. And then we see from his view, he is brought to the home menu. And just to boot up our visualization software, that loads in the HoloLens operating system, kind of gets acquainted, takes some time to generate the spatial mesh, and he sets some options, goes over to a QR code to scan it, which tells the software where the detector is in its own individual space. And then that's all the setup is. So then when it's running, what does he see? So this is a test. First, we'll show you a test with a real-time data acquisition. And so we have the source in the barrel, and we also have the spatial mesh shown. So this is kind of how the HoloLens sees the world around it and the surface around it as these polygons. And originally, it's not within just under a minute of data. It's still taking its time generating and converging onto the source position. And 75, we start to get fairly close. We like, oh, it's in the barrel. And then with about a little over 2 minutes of data, the system is getting close to converging on where the source is. So it's a neutron mode, so it's only looking for neutron sources and is able to kind of figure out there's something in this barrel in about minutes. Yeah. Generally the neutron efficiency of the system is worse than the gamma efficiency of the system. And then there's kind of a display of the other features. So we can switch between gamma imaging mode and neutron imaging mode. So you see at the gamma source, swap to neutron imaging mode, and swaps between the barrels. Like, oh, we're in neutron imaging mode. We know there's a neutron source in that barrel. Awesome. And then we can view the images as well if the user wants to see that. The user can freely move around in the space without any wires, which is great because all the energy is transferred through Wi-Fi to the HoloLens. Yeah, switch to gamma mode, see the gamma image there. Then from there, we have the different options. So you can see a gamma spectroscopy chart if they want to identify the gamma source they're measuring. Yep, easily swap between neutron and gamma mode. You can use this menu, use the spectroscopy chart to kind of identify the source. And also the system has, like the HoloLens just has built-in voice command capability. So if they don't what they want to, they can just say neutron and they can swap between source options as well. It's a pretty nifty piece of software. Okay, but enough of the HoloLens. What if I wanted to figure out, what if I just had like a room full of barrels? And I need to figure out which barrels have the source. And they're just barrels behind each other. And I need to figure out how far away the source is. Or how close am I, right? Because if you're looking for a radiation source, you kind of want to know how far away from you it is, you know? So if we want to figure out how far away it is, we have to use at least multiple imagers, or we just move the same imager at different locations and times. We like move it around on a track, or we just let's see, like basically we just have an imager in one spot, measure for a bit, move it to another spot, measure for a bit, and then input those imager locations within the code we're kind of writing. So then from there, from that position, like from the detector position and the imager data were useless. So like the interaction position in which certain bars, its timing, and other, we can still create those 3D cones we're used to. And instead of projecting it on a spherical surface, we instead kind of pretty much project the cones upon each other. And so when we project the cones upon each other, we have intersections that aren't just on the surface of a sphere, but we have intersections that have not just that have X, Y, and Z position. So we have theta, phi, and R. Exciting, right? And so from there, you can figure out where the source is. And so we have a nice visualization of what that would kind of look like. So we have our two detector set up in position space. We have hotspots generated from projecting the cones we've generated onto each other. And as we can kind of see, we have it placed in, and it's just this demo image to kind of show what it would look like when we get there. And I think that covers it. So, any questions?
Cool. All right. Well, you have a couple questions in the Q&A, so I'll just go over a couple and then I'll see as more trickle down. The first one is, and I saw a couple regarding this, is could you explain exactly what you mean by azimuthal angle? So I guess you give a brief, I guess, a description of what your like frame of references are for your imaging.
Oh yeah. So When working in spherical coordinates, there are kind of, instead of X, Y, and Z, you care about altitude, azimuth, and distance. Because we're dealing with a surface, we just care about altitude and azimuth. Let me see if we can get a good down. This will work. So in for so it can arbitrarily like you can set 0, 0 to be wherever you want. In all of the measurement cases of data we did, we set 0, 0 to be directly in front of the detector. And so imagine you have a sphere around it, and if you're moving horizontally, back and forth, left and right, you will change the azimuth. So in front of you would be 0, behind you would be like negative 180 or 180. Actually, it ends up being the kind of same spherical coordinates. Directly to the left of you would be negative 90 degrees. Directly to the right of you would be positive 90 degrees. And so the range for azimuth is like negative 180 to 80 because you can kind of have 360 degrees around you, right? And then for altitude, it would just be kind of up and down. And this only goes from 90 to negative 90 because it can only really be like one or the other. Just because like if you kind of like you every point can only really have a specific single pot. So if you kind of point up directly up and if you keep going, you would actually be changing the azimuth, not the altitude. So just the azimuth would change and then the altitude would go back down, if that makes sense. But yeah, so it's just like if you're also familiar with spherical and polar coordinates, it would also be like can be referred to as theta and phi. So like theta would be azimuth and altitude would be phi. And hopefully I think that kind of covers it. But yeah, I hope that answered your question.
Cool. Here's another question related more so to like the construction of the HUDPI. So, um, one of the questions is why do you use two smaller crystals, i.e., in this case, cerium bromide, in the system? And then how do you ensure that the crystal properties are similar? And then finally, why do you disregard the ability to do time of flight and or depth of interaction with these readouts?
Okay, good question. So, I guess behind the scenes is that there's a lot of calibration that has to be done with the system. So every detector is calibrated individually. We just take a cesium source and we measure its response. And I think the reality is they're not the same. We have to just calibrate them so they are, because all of these are coupled with optical paths to the SIPM, and slight deviations can affect the percentage of light that gets from the center of the crystal to the SIPM. And so to accommodate, this is a solvable problem. We can accommodate that by just taking a known source. Cesium is our favorite because it's just one single monoenergetic gamma. And then we kind of scale like, okay, we know this photon generates this light output in this detector. So I can say whenever I get that light out, it corresponds to this energy. And we just do that individually for every detector in our system. I think we could do. So the limitations on having like long cerium bromide bars is less of a choice and more of something we just have to do because organic like crystal growth is, from my perspective, still a black magic, and generally it is very difficult to do. And as you kind of get to bigger crystal sizes, it's generally much more likely to get defects, errors. It just generates something that's not usable. Not to mention these are fragile, so you try and cut it and you'll probably break it. And so you just can't get a crystal that big without paying an arm and a leg, several arms and a leg, actually. So, but ideally, if you could get a crystal that long, I think if you're using sodium iodide, you might be able to. It should still be possible to do the same Z position reconstruction. You just have to still have a SIPM mounted at the top and bottom because you have small crystals and we can't put SIPMs close enough to each other. Can't put SIPMs on both ends. We can't really do that in this specific case, but it'd be possible. Let's see. So there was that, and there was a lot there. So why we don't do Z position there? Yeah. Was there anything? So there was that. Was there something? Yeah, go Ricardo. Sorry.
Yeah, the other part of the question was why you don't do time of flight with gammas.
Yes. I would love to, but one is well, actually no, not in this case. It's time of flight with gammas isn't possible because the velocity is always the same. Uh, like they're photons, so they'll always be traveling at the speed of light. And so the kinetic energy equation also doesn't apply because, wait, what's the mass of a photon? Right, they're massless particles. So we just don't have an equation to kind of calculate time of flight to energy of a photon. And also the timing resolution, like even if we could, the timing resolution of this system is about 420 picosecond, which is much bigger than the time of light.
Cool. And last question regarding serum bromide specifically, at least from what I see on the list, is like what's your like effective energy range for these detectors?
Oh, good one. Yeah, it's a bit. So we don't even bother getting signals below 50 keV. And I think traditionally most of like even energies, like even systems that use completely different like detector setups, like semiconductor systems, just kind of struggle to get there. Because I think below 50 keV, that's very like you have a lot of noise, like your the signals you're kind of getting through SIP is also kind of overlapping with noise signals. You actually have to worry about your casing, just they just get attenuated by the casing of your detector, which becomes a major kind of problem. And also just because the energy resolution is just kind of poor, the kind of overlapping signals is just kind of very difficult to image these just and separate them from the noise. So 50 is kind of the low end. And then for the high end, I think we could, like I think as long as our kind of like digitizer is able to kind of image at that pulse height, we don't like we'd see. For this specific case, we have to worry about saturating the SIPM, but we usually don't get that far. Let's see. I guess if I had to throw out a number, it'd generally be like it'd be high to measure something at like 1 to 2 uh MeV for the gammas. For the neutrons, we generally, I mean, you could. I think the problem is that it's very fuzzy what the high range is because you just get less and less efficiency. And you theoretically could, but we just don't really see it. And when you kind of go above 2 MeV gamma sources, they're kind of hard to see. And we do have one available, but that would also destroy our system. So generally, I think I'm just going to throw out 2 MeV for gammas. And then for neutrons, we can go a bit higher because neutron energy and neutrons just have a lower light output range. So I think for neutrons, I can expect to see up to 2 to 3 MeV neutrons. So, but yeah, honestly, we can probably do higher gammas if we just had more serum bromide. There's also the fact that we're limited by the higher energy photons we deal with, the less likely we're to get a photoelectric effect. The higher, like you just need to kind of have a low enough energy for the photoelectric effect to happen. And when you're above 2 MeV, it's just more likely to Compton scatter off the serum bromide. Sorry, yeah. So sorry, it was a pretty big it depends question. So sorry if it was kind of jumbled, but those are kind of the variety of reasons why I think that would be my range. So 50 keV to 2 MeV for gammas and about 50 honestly, probably a bit higher, probably closer to 100 to 150 keV for neutrons, and like 2 to 3 MeV for neutrons. But this is probably system dependent. This can be pushed. Okay, next.
Yeah, we have one question here. Have you considered using any Bayesian algorithms for source localization?
Uh, let's see. This is a really funny one. Like, do I know? I feel like I know you because there's one person doing this that I talked to at a conference. Uh, but I've thought. Sorry. I'm. Okay, but it is possible, but I think there's kind of a lot. It's something I've thought about. It's something I'm honestly not comfortable enough with Bayesian methods to think about. But I'd say if you kind of look into papers made in Angela DeFolio's group, I think you'll kind of find they're kind of leaning into Bayesian stuff with their imaging systems. And Angela DeFolio, yeah, that, that's all I can kind of say on the matter. I've thought about it, but I've it's on the long list of things I want to explore.
So, in the mock inspection scenario that you mentioned in the talk, how does the HoloLens mixed reality process select the correct energy gate for a source, or are energy gates selected by the user instead?
At the time of that demo, energy gates are selected by the user. However, it would be a bit finicky just because of noise and statistics, but theoretically, you could take the gamma spectrum from the serum bromides, find the peaks, and then each of those peaks would correspond to a photo peak, which would correspond to be like an energy you should gate around. And you could set, and the system could automatically set specific gamma peaks. It would be possible. It's work that we just haven't kind of gotten around to doing yet. But at the time of the demo, we set them manually. But if you had a robust enough automated peak finding pipeline and gamma simulating pipeline, it'd be possible. But I'd say this is very much easier said than done. Next.
All right. I've worked with gamma ray imagers, so great to go through the math behind the process. One issue that I've seen in the field is that when working with distributed sources rather than point sources, a strong point source can overwhelm the imaging, and the physically bigger source, which is weaker, is not seen. Have you looked into this kind of problem, or have you only been looking at point-like sources for your measurements?
Let's see. Hmm, let's see. From my experience, I have only looked at point-like sources, but I guess energy gating would probably be the best way to approach it. And then would be the first thing I'd kind of reach to trying to approach a problem like that. MLEM would convergence and MLEM will be a nightmare in those cases. You could also play around with the normalization of the image, um, which also might be a way to help. But it does seem to be a very difficult and valid problem, as you can kind of see from, let's see from here. Like, as you can kind of already just see in just our 2 point sources or effective point sources, we already have the Pooby just kind of overtaking this California. And if you aren't able to energy gate it, it is probably a very valid and difficult problem to solve. Uh, but yeah, I wish you luck in your work. I'd be interested to see how you solve that problem.
How can this be used as handheld, as it is connected with many electronics as seen in the pictures? I was just curious.
Ah, you got it. Okay. Now this is this is it'll eventually be handheld, but I can kind of dive into that. That's kind of where I'm going with my side of the research. So, um, right now, if you want to do so, the power draw of a SIPM is only like to bias this detector, I only have to go up to 29.6 volts. That can be done at a battery. That's one of the wires. The majority of these wires are going to a bulky digitizer. And for what we're trying to do, a digitizer is overkill. Digitizers are kind of meant to boost signals and to do all sorts of different like pulse integration, like just be a full pulse integration processing suite. Very useful if you're in the lab in the research and you want to characterize and troubleshoot a system. Not very useful if you want to move it somewhere. However, there's a simple answer there and just making a simple circuit. So you can make an ASIC, which would just be an application-specific integrated computer, and all it would do would be just process individual signals and just have one of those for each channel. Research has been done on that, but as you can kind of expect, not only are not only are integrated circuits incredibly expensive to make, they have a lot of issues, a lot of troubleshooting. Each shot requires tons of money to kind of do. And an initial few tests have resulted, oh, there's reduced PSD capability. The way I'm kind of going for is I'm going to go for FPGAs, field programmable, I think, gate, FG, FPGAs, field programmable gate. Ah, that last part's getting me. But those are a bit more programmable and easier to work with and are a little bit less expensive to iterate upon. And what I would do is that I found out that instead of using PSD to discriminate neutrons from gammas, I can effectively just use time of flight. So I can avoid that problem. And I could just with time, like just using with a system that is significantly good at, has a sample rate that can be a good enough time resolution. And I could just even use something simple that just measures the pulse height. I would still be able to image on a much simpler, less power hungry, and a lot smaller source. But if we also just had like 2 detectors in here, we could use a much smaller box that just puts it in there, run that on battery, and then it'd still be kind of handheld. But we're getting to having a handheld system, but in our current state, it's just much more convenient and much easier to characterize with this kind of connecting it to the big data acquisition equipment. I hope we didn't drone on to there, but I hope that answers your question.
All right, we'll do one more since we're getting on time here. And there's a lot more questions that we didn't have a chance to go through, so feel free to take a look at them, Will, whenever you have the chance. Otherwise, the last question that we'll go over here today is, have you tried any Monte Carlo techniques to compare with the actual experimental results? If so, how close was the imaging?
Oh man, this is a better question for Ricardo than me, to be honest. But I think, well, it's a funny question because you just have to simulate. Like I've made actually, what is it, tens, and we'll probably eventually probably have hundreds of these simulations of this system in MCMP by the time I graduate. Like I think like the easiest way to kind of validate and write papers on, but what you actually see is just creating a Monte Carlo simulation. I would say like doing this work and doing Monte Carlo simulations of your system just to see if like, oh, is like this physics why I'm getting this issue are just integral. I think MCNP is just great for kind of getting efficiencies and count rates. If you want to dive into kind of the photon stuff, I like some base experience in JON4 and done some work there, but JON4 is a whole nother beast compared to MCNP. But I would say, yeah, MCNP or like something similar that's more available to international communities would be something you just want to do just to kind of trouble just not even if, maybe if just for troubleshooting, but also for comparing your results to something else, kind of see if what you expect to happen is what you measured, what you expected to happen, and what you simulate actually all match up, which is just what you kind of want to do for a paper. And also just kind of seeing design properties, because I've ran simulations where I've added more bars to see how much my event rate would kind of go up too. It'll be very important just for kind of designing as well. Yeah, but Monte Carlo is kind of good, kind of core to this work.
Cool. And with that, we'll close today's lecture. So thank you everyone for joining. We'll see you all again tomorrow for tomorrow's talk. Thank you.